Now welcome to the fifth segment of this playlist, which is about resolution of vectors. So now let us start the next segment, which is a resolution of vectors. So what is resolution of vectors? The method of splitting up of a vector into vector components along the coordinate axis. So if we have a vector in any randomly oriented direction, we split that vector into three parts. Each of those parts will be along the direction of the coordinate axis. So one of the component will be along x-axis, one of them will be along y, and one of them will be along z. These three components along the three coordinate axes are called the rectangular components, thereby representing a vector in terms of sum of its rectangular components is called a resolution of a vector. So we first split a vector into the three rectangular components along the three coordinate axes and then represent the vector as the vector sum of these three components. That is called resolution of a vector. Okay. Now let us see how to do that in two dimensions. So resolution can be done in two dimensions, resolution can be done in three dimensions also. So in two dimension, first we need to do is we have to parallelly shift a vector. Okay, we have to parallelly shift a vector. So if a vector is, say, this blue colored line is a vector A, say, so it is somewhere around here. Now what we have to do is we have to parallelly shift the vector to such a position that one of its points, that is the starting point, fits the origin. So the starting point now fits the origin, and we can write here this is the point where it fits. Okay, this is basically the origin, okay, where one end fits, and the other end is at a point P. Okay, this is the direction of the vector, and this point is, say, okay, let us name this as A, or say let us have this as the point P. Okay, this is the point P. Now this OP vector is basically equal to the A vector. Okay, this is the A vector. So step 1 is first we have to shift the vector parallelly to the origin. One end should be at the origin. Step 2 is find out the angle that this vector makes with x-axis. Okay, if the angle made with x-axis is theta, then the angle made with y-axis will be 90 minus theta. So we need to measure the angle that this vector makes with x-axis in the anti-clockwise direction. Okay, if this is theta, then here this angle in the anti-clockwise direction, this will be 90 degree, this will be 90 degree minus theta. Okay, that angle will be 90 degree minus theta. If this is theta, this is 90 degree minus theta. That was step 2. Now step 3, we have to find out the basically the scalar component of this vector A vector, which is OP vector, along x-axis and along y-axis. So name this point as M and name this point as N. So we need to find the length of this OM and the length of ON. OM is basically the scalar component of vector A along x-axis. Okay, the scalar component of vector A along x-axis. So the scalar component of vector A along x-axis, for that you can consider the triangle OPM. Let us consider the triangle OPM. Now in this triangle we have the angle theta. So this cos theta will be base by hypotenuse. So base will be OM and hypotenuse is OP. So we can write here OM is basically OP cos theta. Now what is OM? OM is basically the scalar component of this vector A along x-axis. So that is denoted by AX. So this length O to M, this is called AX, and similarly the length from O to Y, this is called AY, which is the scalar component along y-axis. So we are first concentrating on the scalar component along x-axis, so which is AX, that is equal to OP. Now what is OP? OP is the magnitude of this vector A. OP is the magnitude of the vector A. So it can be simply written as A in place of OP, and it is cos theta. So AX is equal to A cos theta. Okay, AX is A cos theta. Now similarly, let us find in the triangle OPN. Okay, in triangle OPN. Okay, now in the triangle OPN we have the angle 90 minus theta. Okay, we have the angle 90 minus theta. So if we consider cos 90 minus theta, so if this is the angle, this one is going to be the perpendicular, this is the hypotenuse, and this ON is the base. Okay, and cosine is always base by hypotenuse, so it is ON. I'm talking about the triangle OPN. Okay, OPN, in it base is N, because 90 minus theta is the angle. Okay, so the side attached to the angle is the base, side opposite to the angle is perpendicular, and the bent one is the hypotenuse. The longest side is the hypotenuse in a right angle triangle. So cos 90 minus theta, base is basically ON divided by hypotenuse, that is OP. So from here we can write ON is basically OP. Now cos 90 minus theta, which is this cos 90 minus theta, can be written as sin theta. Okay, we know it from the complementary angles. Cos 90 minus theta can be written as sin theta. So instead of cos 90 minus theta, we can write here directly, we can write here as sin theta. Now what is ON? ON is basically this AY, the scalar component of the vector A along y axis. So AY, and OP is again the length of this vector A, or the magnitude of the vector A. So simply we can write A sin theta. So AY will be A sin theta and AX will be A cos theta. So the horizontal component, or the scalar component along x axis will be A cos theta, and the scalar component along y axis, or the vertical component, will be A sin theta. Okay. Once we have found out the scalar components along x axis and y axis, the next task is to find out the vector components, and finding that is very easy, because we know we have the unit orthogonal vectors. Along x axis, this unit orthogonal vector is I cap, and along y axis the unit orthogonal vector is j cap. So we multiply the length of this OM with I cap to get the vector component along x axis. Okay, so we basically multiply the length of this vector OM with I cap, that is OM is modulus AX vector into I cap, that is AX I cap, which is A cos theta into I cap. That gives us the vector component along x axis. Similarly, vector component along y axis will be magnitude of this ON, which is mod AY vector multiplied by the unit vector in that direction. So AY j cap. So the vector component along y axis will be AY j cap, or it will be A sin theta into j cap. So we have found out the scalar component, which is A cos theta I cap, which is the vector component along x axis, and vector component along y axis is A sin theta into j cap. Okay. With that, let us go to the next part. So once this vector components along x axis and y axis are known, we can simply add them vectorially, of course, to make the complete vector A. So it can be written as AX I cap plus AY j cap. So we can simply write A cos theta I cap. We can simply write it A cos theta I cap plus A sin theta j cap, and we add them, then we get the total vector A. Okay. So this is basically a x vector along x axis, this is a y vector along y axis, and this is a vector, and this a vector is basically equal to a x vector plus a y vector, and this a x vector is A cos theta I cap, A cos theta I cap, plus a y vector is basically A sin theta into j cap. Okay. Now the magnitude of this A, magnitude is very easy. We have to just square and add the magnitudes. Okay, so from here to here this distance is AX, so the magnitude will be square root of mod AX vector plus mod AY vector. So just square and add the magnitudes. Okay, so this magnitude is AX, so this is simply, we can write AX, this length, and simply this height, this length is AY. Okay, this length is AY, then this is also AY, this part is also AY, this part is AX, and the hypotenuse will be, by Pythagoras theorem, square root of AX square plus AY square. Okay, that gives the magnitude of the resultant vector, that is the vector A. Okay, the total vector whose magnitude is root over AX square plus AY square. Now the direction, okay, we have to also define the direction. Now how to define the direction? To define the direction, what we need is angle. We know that very well. To define, we need angle. Okay, so what is the angle that we are talking about? This is the angle that we are talking about, the angle that the vector makes with x-axis. If that is theta, then we can know cos theta will be base by hypotenuse. So what is base? Ax, x component, and hypotenuse is the total vector, magnitude of that vector. So it is Ax by A. So you can see cos theta is Ax by A. So theta can be written as cos inverse Ax by A. Okay. So theta can be written as cos inverse Ax by A. Okay. Now to know what I am writing, what is about the inverse trigonometric functions, you can check the other videos that is available in YouTube from my channel, where I have told in details about the inverse trigonometric functions. Okay, next similarly, if we consider sin theta here, which will be perpendicular by hypotenuse, so which will be AY by A. So here theta can be also written as sin inverse AY by A, and also we can write the angle in terms of tan theta. So tan theta is perpendicular by base, perpendicular is AY, divided by base is AX. So we can write here theta as tan inverse AY by AX. Okay, theta will be tan inverse AY by AX. So in this way, in two dimension, basically we can split a vector into its rectangular components along x and y axis and represent them as a sum of the vector component along x axis and vector component along y axis, find the magnitude, and then find the direction. Okay, so now we'll see a numerical example of this one. So as you can see on the screen, this one, this question is here, where a box is pulled upwards by a force of 60 Newton as shown in the diagram. Then consider some suitable coordinate axes and find the following things. Okay, the angle that F makes with x axis. So first we need a coordinate system. So how to make a coordinate system? A coordinate system is best built in such a way that the measurements are very convenient. Okay, so normally when only one force is applied or some movement is happening from one point, like a starting point or a ending point or the point of application of force, these points should be made the origin, okay, to make the calculation simpler. So here the point of application of force is right here. Okay, so we can the point of application of force is right here, so we can make it the origin. Okay, we can make it the origin, and okay, so this will be the x axis. Okay, this will be the x axis, and similarly this will be the y axis. Okay, this will be the y axis. So x axis and y axis can be drawn here. So this is x and this one is y. Now this angle is 60. So what is this angle? This angle has to be 30 degree. Okay, so angle that it makes with x axis will be 30 degree. So let's write that. So question number 1, answer to that, angle that F makes with x axis, that is theta, equal to 30 degree. Number 2, the scalar component of F along the coordinate axis. So what is the scalar component along the coordinate axis? So let us see here. What will be the scalar component? We have to just draw a line. This one will give you the scalar component along x-axis, draw a perpendicular in y direction, and this one will give you the scalar component along y-axis. So this is basically can be written as fx, and this can be written as f suffix y. So first let us find what is fx. Okay, so scalar component along first x-axis. So we know scalar component along x-axis will be f cos theta. Okay, it will be cos theta. Theta is the angle it makes with x-axis, which is 30 degree. So what is f? F was 60 cos 30. Okay, so 60 cos 30, which will be basically root 3 by 2, and that is ultimately 30 root 3. Okay, so this value is 30 root 3 Newton. Scalar component along x-axis. Similarly, we can find the scalar component along y-axis, scalar component of f along y-axis, which will be f suffix y, which is f sin theta. Okay, now f is 60 and sin 30. Okay, sin 30 is basically half, so this will be 30 Newton. Okay, so that will be 30 Newton. So the scalar component along y-axis will be 30 Newton, along x-axis will be 30 root 3 Newton. Now, what we have to find out is the vector components along the coordinate axis. Fine. So the vector components finding is very easy. Along x-axis multiply with I cap, along y-axis multiply with j cap. So vector component along x-axis, that will be fx I cap, which will be basically 30 root 3 I cap. Okay. Similarly, vector component along y-axis will be fy into j cap, which is 30 j cap. You can write Newton after this, because in individual axis direction also it's still a force, so it's a part of a force, so you can write it Newton out there. So the vector components along the coordinate axis will be 30 root 3 I cap and 30 j cap along x and y axis respectively. Now the next question is the vector f in terms of the unit orthogonal vector. So you have to basically add these vector components to write the total vector. Okay, so after the vector components along x and y axis is found out, now we have to find the vector f in terms of the unit orthogonal vectors. Okay, so let us write the vector f in terms of unit orthogonal vectors. Okay, that f will be basically fx vector plus fy vector. Okay, so fx vector was basically it was 30 root 3 I cap plus it was 30 j cap Newton. That is the force represented in the vectorial form, 30 root 3 I cap plus 30 j cap. Then what we had to find was magnitude of the vector and direction of the vector. So next is magnitude of vector f. Magnitude of f vector, which will be mod f vector, just square and add under a square root these components. So the x component is 30 root 3 whole square, and then we have 30 square. So inside square root, a 30 square will be taken common, then root 3 whole square is 3 plus 1, so that is 4. Ultimately 30 comes out and 2 comes out, so that makes 60 Newton, which is equal to the value that was given in the question. So magnitude of F is equal to 60 Newton. Now the direction of F. So direction of F you can represent in terms of theta. Okay, so theta was basically, so direction of F can be written as, so we can write here cos theta is basically Fx by F, x component by F, as we have seen. So Fx is basically uh, Fx is basically 30 root 3, and F is the total force, which was 60. So that makes root 3 by 2. So if cos theta is root 3 by 2, theta will be uh, basically 30 degree. Okay, so that will be the direction. Okay, you can write this is the direction with respect to x axis. Okay, so with respect to x axis the direction is 30 degree. So this is how we can solve the numericals related to resolution of vectors in 2 dimensions. Okay, what we had done was, first there was the force, found out the angle that it makes with x axis, then found the scalar components as the x component will be f cos theta, y component will be f sin theta, vector component is just multiply the x component and the y component with I cap and j cap. Then the vector was written in the by using the unit orthogonal vectors, that is the vector components, then the magnitude of the vector, and finally the direction, which we can use cos theta, sin theta or tan theta. I have used cos theta here for finding out the angle that the vector makes with x axis. Okay, so that is how we do resolution of a vector in 2D. So now we will be seeing how to resolve a vector in 3 dimensions, that is in space. So the step 1 is very simple to what we did in 2 dimension. You have to parallel shift the vector from any point to a point such that one end is fixed at the origin. So if this blue colored thing is the vector, we have to shift this parallelly to such a position that one end fixes on the origin, and we need to find out the coordinates of the other end. Okay. So now, as this vector has been fixed with one end at the origin, this is the origin here. So now, from here we need to find out the step 2, that is the angle that it makes with x, y and z axis. Okay. So in 2 dimension only having the angle with x axis was enough, but in case of 3 dimension we need to know the angle that it makes with x, y and z axis, the three of them. So this is our x, this is our y, and this is the z. So here the angle is always measured in anti-clockwise direction. Remember that angle measured in anti-clockwise direction is positive, and angle measured in clockwise direction is negative. So alpha is basically the angle that this vector makes with x axis. Okay, so we need to start from the x axis and end on the vector. This is equal to alpha. Okay, this angle is alpha. Now we have to start from the vector, end on the y axis. This angle is equal to beta. Similarly, we have to start from the vector and end on the z axis, and that gives us the angle gamma. Okay, so we have alpha, beta and gamma, these as the three different angles that it makes with x axis. So now this is the origin. Say this is the point P, which is here. Now let us join these points basically to make it a complete look. Okay, to give this box a complete look. So we are joining these lines here so that you can understand from where the vector is. So you can see O is one of the corner of this box and P is the another corner. Okay, so this OP is also called the solid diagonal. Okay, from the one corner to another, crossing through the volume. Okay, so once we have got the angles alpha, beta and gamma that the vector makes with x, y and z axis, now we have to find out the scalar components. Okay, we need to find out the scalar components along x, y and z axis. So the scalar component along x axis will be basically this length from here until here. Okay, So let us name this as say this is M. Then from origin to this point on the y-axis, that will be the scalar component along y-axis. So let us also join that with a line. This is the point N, and say this is the point R. Okay, this is the scalar component along z-axis. Okay, scalar component along z-axis. So these are the three components. So now how to find out this component along x-axis? So for this you do not need to have any proof, but we just need to remember how it comes. So basically this scalar component along x-axis, is basically ax, which is equal to OM, and that will be denoted by, so first let me tell you, from O to P this is basically vector A. Okay, this is basically vector A, and so O to P, this length is mod vector A. So coming back to here, the scalar component of this vector along x-axis, this OM, will be basically magnitude of this total vector, which is A followed by cos alpha. Okay, as we are taking with x-axis, so we have to also consider the angle that the vector makes with x-axis. Similarly, if we need to find the scalar component along y-axis, so scalar component along y-axis is ON. That is the scalar component along y-axis. Okay. So now how to find out this? For this we will be requiring the angle beta, because we are finding out the scalar component along y-axis. So it will be magnitude of the total vector multiplied by cos beta. Also we have to find out the scalar component along z-axis, which is OR. Okay, that will be known as AZ. Okay, which is equal to OR, and that will be basically the vector A, the magnitude of vector A, multiplied by the cos of angle that vector A makes with z-axis. Okay, so the vector A makes with z-axis an angle of gamma, so it will be AZ equal to A cos gamma. Okay, so AX will be A cos alpha, AY will be A cos beta, and AZ will be A cos gamma. Okay, this is also shown here in the step 3, these three things. Now you need to find out the vector component. So to find vector component is not that difficult. We need to just consider the unit vectors, the unit orthogonal vectors. So along x-axis, we have unit orthogonal vector I cap, along y-axis we have unit orthogonal vector j cap, and along z-axis we have unit orthogonal vector k cap. Okay, so multiply this component with I cap, we will get the vector component along x-axis. Multiply this with j cap, we will get the vector component along y-axis, and multiply this with k cap, and we will get the vector component along z-axis. Okay, so which is being shown here, I cap, j cap, and k cap. Okay, multiply with the unit vectors to get the vector components. So once the vector components are found out, now what we need to do is write down the total vector. So the total vector will be basically the sum of the vector components, that is AX vector, AY vector, and AZ vector. AX vector is basically A cos alpha into I, Y vector is basically A cos beta into j cap, and AZ vector is basically A cos gamma into k cap, as we have seen. So this will be our thing here, which we need to remember, that is how to resolve a vector into its components. So if we have a vector whose magnitude is A, angle that it makes with x-axis, y-axis, and z-axis are alpha, beta, and gamma, then that vector can be resolved into the rectangular components A cos alpha I cap, A cos beta j cap, and A cos gamma k cap. So this A cos alpha, A cos beta, A cos gamma, all these are the rectangular components because they are acting along the three different coordinate axes. Now the magnitude of the vector A, that will be basically equal to the mod vector A, which is basically the square root of the scalar components. We have to just square the scalar components and add them and take the square root. That will give us the magnitude of the vector. Then we need to find out the angles, okay, the direction, it is very simple. As I have told you, it will be done from here. So ax is a cos alpha. We had some relation like that, if you can remember. So here ax was basically a cos alpha. So from here cos alpha is ax by a. Similarly, cos beta will be the y component, ay by a, and cos gamma will be basically az by a. Okay, just look at the relation that I had written previously. Ax is a cos alpha, ay is a cos beta, and az is a cos gamma. So just find out cos alpha, cos beta, cos gamma. You can take the inverse of this to find the angle. So if cos alpha is ax by a, we can write alpha will be cos inverse ax by a. Similarly, here beta will be cos inverse ay by a, and similarly cos gamma, from there gamma will be cos inverse az by a. Okay, in this way we can find out the angle that it makes with the three axes. Now one thing that is not written here, but you should remember, I am writing this now, this relation which is very important, that is the angles. These angles has got a relation between them. Firstly, we need to know this cos alpha, cos beta and cos gamma, okay, are called the direction cosines. Okay, these are called the direction cosines because these define the directions and they are cosines in nature. So the cosine functions, so these are called direction cosines, and these direction cosines have got a important relation. Please write this one, don't forget to write this. The direction cosines relation is that if you square one direction cosine, that is cos square alpha, add this with the cos square beta and add this with the cos square gamma, the result is going to be 1. This is very vital, this is very important. This is the relation between the direction cosines of a vector in 3 dimension. If we square and add the direction cosines, the result is going to be 1. This relation is very useful in numericals also, like if you are given the value of the angle alpha, if you are given the value of the angle beta, you don't know the angle gamma, you can calculate that easily from this relation. So it can be otherwise also, alpha gamma can be given, beta can be found out. So basically if you are given two angles, any two angles that the vector makes with either x or y, y or z or x. So basically you know two angles, you need to find out the third angle, you can use this relation which will be very useful. Okay. So with that, now let us go to the numerical example of a 3D situation. Okay. So we will be doing the 3D situation here. So the 3D situation is very as shown here. This is basically a box. It can be thought of a room. So the problem is like a mosquito moves from the corner O of the room to the corner E as shown in the diagram. Choose suitable coordinates and then do the following. So the mosquito has moved from O to F through a straight path. It could have been through a bent path, but here it happened through a straight path. So first we need to find out is the scalar component of the displacement along the coordinate axis. So we need to find out what is the scalar component of the displacement. So we need to find out basically this vector, okay, OF vector, which is basically the displacement vector. Okay. So let us proceed. First let us write OF vector. So this OF vector will be basically we will have a component along x axis, component along y axis and component along z. So this is our x axis, this is our y axis, this is our z axis. Okay. Now let us draw the components out here. Okay, let me use green color. So starting from O until this point A, this is the scalar component along x axis. Starting from O ending at C, starting from O ending at C, okay, this gives the scalar component along y axis. Starting from O ending at D, this gives the scalar component along z axis. Okay. So this is basically x component OA vector, OC vector is y component, OD vector is z component. So let us write that this OF vector is basically OA vector plus OB vector plus OC vector. Okay. Sorry, OA, OC and OD. Sorry, OA, OC and OD. Please forgive me. This is OA vector plus OC vector plus OD vector. Okay. Now this OA vector is along x-axis. So we will be, you can see this length is 10. Okay. This length is 10. That means this is also 10. OA is also 10. This is 5. So you can see OD will be equal to 5. And this one is 8. So this OC will be equal to 8. Okay. So along x direction, this OA vector will be 10 I cap. Basically, it's going to be 10 I cap. So you can write it as 10 I cap plus OC. OC, that is along y axis, that is 8 J cap plus OD is basically 5 K cap. Okay, that's it. That's the complete vector. Now let us come back to the solution. So what they are asking first is scalar component of the displacement along the coordinate axis. Number 1. Okay, so the scalar components along x, y and z axis. What is this component? So x component is 10, y component is 8 and z component is 5. So these are 10, 8 and 5, okay, respectively. These are 10, 8 and 5 respectively. Number 1. Next is the vector components. Okay, so again vector components along x, y and z axis are, what are those? As you can see, 10i, 8j and 5k. Now you have to write using the vectors. 10i, sorry, it will be 10i cap, 8j cap and 5k cap. Okay, that will be the vector components along the 3 axis. Then the displacement vector OF, we have already found that out. Displacement vector OF is basically 10i cap plus 8j cap plus 5k cap. Then the magnitude of OF, displacement vector OF, so that is mod OF vector. So it will be square root of this 10 square plus 8 square plus 5 square. Okay, so that is 100, 64 and 25. So 184 and 189. So it will be square root of 189. Okay, that will be it, square root of 189. This much units you can say, or sorry, it will be meter because it's shown. You can see all the dimensions are shown in meter, 10 meter, 5 meter, 8 meter. So the answer here is going to be meter. So this will be the magnitude will be in meter. So direction of OF. Now to find out the direction of OF, you need to find the value of alpha, beta and gamma. So point this out. So this will be alpha out here. This will be beta. And this angle is going to be gamma. Okay. So cos alpha, cos beta and cos gamma, these are the three things that we will find out. Cos alpha will be ax by a. So remember this thing is like the x component 10. This is like fx, this is like fy, this is like fz. Okay, and the modulus is this one, square root of 189. Okay, so let us find out the alpha, beta, gamma. So 10, 8 and 5. So it is 10, 8 and 5 and square root of 189. So it's basically 10 I cap plus 8 j cap plus 5 k cap. That is the OF vector. okay, and the magnitude was square root of 189, okay, square root of 189. So we can write here cos alpha. So we can write here cos alpha is basically 10 divided by root over 189. So here alpha will be cos inverse 10 by root over 189. You can use calculator to find this one. Similarly, cos beta will be equals to 8 divided by square root of 189. So angle that it makes with y-axis will be cos inverse 8 by root over 189. Similarly, the angle that it makes with z-axis cos gamma can be shown by 5 divided by root over 189. So here gamma equals to cos inverse 5 by root over 189. So these three angles, that is cos alpha, cos beta and cos gamma, from here what we get, alpha, beta and gamma. These three angles are the angle that it makes with x-axis, y-axis and z-axis. This is the angle with x-axis, this is the angle that the vector makes with y-axis, this is the angle that the vector makes with z-axis. All this in the anti-clockwise direction, that is the positive. So you can use the calculator and find the value in degree or radians, and in that way we can basically solve our questions that will be related to the resolution of a vector in 3 dimensions. So here what we have done, we have just tracked down the flight of a mosquito from one corner of the room to another. We have found out the displacement vector, found the scalar components, vector components, the magnitude of the vector and the angle that it makes with the 3 axis, which is the direction of the vectors. So with that, basically this segment of resolution of vectors comes to an end. The next segment will be types of vectors.